So I will talk about the nature of energy exchanges in the ocean and how that varies across different length scale. The first thing you might object is, what's so special about ocean? It's just salt water. And if you take a scuba dive, you'll see something like this. This is the ocean, but it essentially looks like a glorified aquarium. So what's very so special about this? Why can't we study flows in the aquarium, generalize that to the ocean? And the answer to that is that if you zoom out, you see flows which look like this. Now, this is across thousands of kilometers, and each individual circles called the eddies are hundreds of kilometers. Not only they are there, they evolve, they are stable, and they stay there for days, months, sometimes years. This is not seen in the aquarium or even when you take a scuba dive, but this is seen rather on the surface of the soap bubble. So if you take study flows on the surface of the soap bubble, which is basically 2D, you will see that these large-scale structures are stable. So the ocean, which is essentially 3D, why does that behave like a 2D flow? Out of context, the largest such stable structure is this eye of Jupiter that you might see in famous NASA image, and that is similar to these eddies that are found in the ocean. Now you might say, okay, in these length scales of thousands of kilometers, the depth of the ocean is very little. So ocean is basically 2D, so it's natural that the flows will behave like 2D flows. The answer is that it's true, but not quite. So the way that these eddies survive is by force balances, and there are two kinds of force balance. The first, where the horizontal pressure gradient is balanced by the Coriolis force, and the second is where the vertical pressure gradient is balanced by all the fluid above a certain layer. The first is called geostrophic, the second is called hydrostatic balance. The fact is this balance with Coriolis force can only happen if you're in a large length scale, and that's natural because if I throw this chalk up, the trajectory of the chalk is very weakly modified by Coriolis force because it didn't go far enough. The rotation of the earth is not high enough. So Coriolis force can only act on large length scale or if the rotation is large. There's a non-dimensional number called the Rossby number, which measures how impactful the Coriolis force is. And at very large scale, where the Rossby number is low, the flow looks something like this. There are cyclones and anticyclones given in red and blue. They merge together, they form bigger cyclones and anticyclones, and they are sustained there for a long time. This is happening in 3D flows, remember, not 2D ones. But there is another question. Just because there is a balance, will the flow go towards it? It can be an unstable fixed point. And the answer to that is that if the Rossby number is very small, the equations, as we'll see later, correspond to 2D turbulence equations. And that's why we see similar structures. So this brings us nicely to the equation, which is basically Navier-Stokes, but certain approximation and assumption. You go to a rotating frame, you assume that the variations in latitude and longitude are small, and that's why you saw a box earlier, not a whole sphere. You restrict to a small regions of latitude and longitude. Also, you assume that the stable part of the flow is when heavy water is at the bottom, light water is at the top, which is very natural. And the equations look something like this. Don't pay much attention to it, apart from the fact that the Rossby number is multiplied with the nonlinear terms. Your u is the horizontal flow velocity with two components. W is a vertical flow velocity. B is a buoyancy, which just ensures if lighter water gets below, it is pushed back up, and if heavier water gets on the top, it's pushed back down. And alpha is the aspect ratio, like how wide the ocean is compared to its depth. In this case, it's 20. For context, this is like 15:1 aspect ratio, so it's around 1.5 times this. The boundary conditions are periodic in X and Y direction, just for the details, and it's free slip at the top and the bottom layer, which doesn't allow flow to escape in the vertical direction. Now, there's another interesting quantity called potential vorticity PV, which we'll discuss now. And for Rossby number very small, close to 0, this PV acts like a tracer. If you have followed Mayank's talk, you know what tracer is. Basically, tracer follows the fluid equation. And this is very similar to 2D turbulence, where the vorticity, which is a single component in 2D, follows the fluid in case of non-forcing inviscid 2D turbulence, that is. And the formula for vorticity and potential vorticity looks very similar, except for this buoyancy. And just like in 2D, where you can, if you know a vorticity field, you can get a flow field. In this case, if you know a potential vorticity field, you can get back a flow field, which is in geostrophic and hydrostatic balance. So essentially what I showed you earlier is basically this Q field for small Rossby number, and looking at that, you can track what the flow is doing. Now, when Rossby number is non-zero, it's finite, such inversion doesn't give you the entire field, because the entire field is not necessarily in this balance, but it gives you the part of the field that has the balance, hydrostatic and geostrophic balance. So looking at the potential field, potential vorticity, sorry, you can get what the balance flow is doing. And because the eddies are in balance, you can know what the eddies are doing by looking at the vorticity. So there is another thing in the ocean is that it needs constant supply of energy. Otherwise, the flow will just dissipate and die out after a long time. And there are two sources of energy, tides and the wind. So the winds blow over the ocean, causing the ocean surface to disturb itself. And these are called inertial oscillation, which feeds energy into the ocean. Similarly, the tide bulge, when moon goes around the earth, follows the moon around. And so the tide slips over this surface of the earth, and when the tidal flow encounters the rough topography of the ocean, it gives off more energy is dissipated. And these generate what are called internal waves. This is another part of the flow apart from the eddies. So ocean flow has two parts, balanced, which are mostly eddies, and unbalanced, which are mostly waves. And we are asking, how do they interact each other? How do they exchange energy at different length scales? Now, for the further context of the talk, the waves will come from the tides, not the winds. And the Rossby number we'll be dealing with are 0.1, which scales around 10 to 100 kilometers, and 1, which is around 1 to 10 kilometers. So if you look at the Rossby 0.1 flow, you see the eddies. Now this is PV at this particular horizontal slice. I'm not showing you the entire three-dimensional flow. You see that these eddies are disturbed by the tides. There are both tides and eddies in the flow, but this only looks at the eddies. But they evolve slowly, but they don't break, they remain. There were small oscillations. If I go back, there are small oscillations, but they don't break. They sustain and they evolve like you saw in the previous 3D flow. So those are the conclusions, slow evolution, and the eddies remain stable. However, if you look at Rossby 1 flows, the eddies break down catastrophically. It's a small scale flow, eddies break down, and it's a very fast evolving flow. So eddies are destroyed, and it's fast evolution. The only change in these two cases is the Rossby number. And now you can tell me that this is obvious because you increase the Rossby number 10 times, which means you increase the nonlinearity. And if you increase the nonlinearity of the system, there will be more interactions. Tides will try to break the eddies. It's right. And if you see this plot, this is the energy spectrum, horizontal energy spectrum. Tides are forced here, while the eddies are forced here. And they generate energies far away from their forcing range, which signifies nonlinear interactions. And this is true in Rossby 1.0 because it's nonlinear, but this is also true in Rossby 0.1, that wherever you force tides and eddies, there are energies farther away from it, which means that there are nonlinear interactions, but among eddies themselves and tides themselves. Tides and eddies don't interact with each other. And this is confirmed if you look at the transverse plot. This is the energy transfer rate, the nonlinear energy transfer between only eddies and the tides. And you see for Rossby 0.1, which is on the left, versus Rossby 1, which is on the right, Rossby 1 transfers is around 10 times larger than Rossby 0.1 transfers. The amplitude is natural because the nonlinear term has risen by 10 amount when you increase the Rossby number. But what is interesting is the signal for Rossby 1.0, it has more irregularities. Sometimes the crest and the troughs are closer together, sometimes they're far apart, whereas this is more regular than this one. What I mean to say is that there are more timescales in the flow, which is confirmed if you plot a frequency spectrum. So this is a frequency spectrum for Rossby 0.1. This is a forcing frequency of the tide, and you see there are only harmonics of these forcing frequencies, which demands that this tide only interacted with itself. So the omega t wave interacted with itself to give 2 omega t and omega t interacted, 3 omega t, 2 omega t, 2 omega t interacted to give 4 omega t, and so on and so forth. The other frequencies are very little compared to these peaks, which are harmonics of the flow, which means tides only interacted with itself. Whereas if you look at Rossby 1.0 flow, yes, there are harmonics, tides do interact with themselves, but there are other frequency peaks, 0.5 omega t, 1.5 omega t, which are not harmonics of these tidal frequencies. This signifies that tides interact with themselves and also the other flow structure, which are the eddies, to give rise to a spectrum of energy in the higher frequency regime. And this causes the eddies to break. This interaction between tide and eddy at Rossby 1.0 by forming the frequency spectrum causes the eddies to break. So I'll conclude by saying that at Rossby 1.1, although nonlinearity weak, there is interaction, but it's separated between tide and eddy interaction. Eddy and tide don't interact with each other. Whereas Rossby 0.1, there is additional tide-eddy interaction, which generates this frequency spectrum that we saw earlier, and that breaks the eddies. With this, I'll finish the talk and take any questions you might have. Thank you.
Thank you, Rajarshi. Yeah, any questions you can ask away.
Like, given a signal, how do you actually separate the eddy and the...
Excellent question. So by calculating this, so we separate the balanced and the unbalanced flow by first calculating the, if you give me the full signal, I calculate this potential vorticity Q, and I invert this potential vorticity to get the balanced flow. And the rest will be the unbalanced part.
The vorticity gives you the eddies, and then you just subtract.
Subtract, simple subtraction.
But from the power, when you do the power spectrum, it's the full velocity field, right?
Yeah, the power spectrum is the full velocity field.
And those peaks you said correspond to the tides.
Tides, forcing tides. It's around 1.7.
How do you see that, and why is it not the eddy that is?
Because the eddies were, if you do a simulation without the tide, the frequency spectrum will have a peak around 0 and it will decay. So eddies, because they're balanced, they have very small evolution timescales, very low frequencies. Sorry, very large evolution timescales, very small frequencies. So that's why they directly don't come, but they can come through interactions, which you see at Crosby-1. Any other questions?
Rajarshi,
Samriddhi is asking something. Yeah.
you were mentioning the length scales in the problem corresponding to the Rossby. So are these length scales the Zeeman length scale in the problem? I mean the length scale where the rotation and the nonlinear thing is balanced?
No, this is a physical length scale, the entire length scale of the domain. So if you want to go to the physical domain, you multiply your horizontal length scale by 100 kilometers for Rossby 0.1 and 10 kilometers for Rossby 1, and you get the physical domain.
But how is the Rossby number setting the length scale? So that part.
So there's a typical flow scales which vary around from meter per day to few hundred meters per day to few kilometers per day. If you fix the latitude, you have a frequency. In this case, this is a slightly above 30-degree latitude, and then you get the length scales.
Okay.
Kaustubh has a question.
Yeah. Initially, you started with saying that the ocean is not quite 2D, right? I mean, you gave a good reasoning for why we see these 2D-like features. But as a lesson, what can I learn that through the simulations for the ocean not being 2D and actually having some 3D aspects? Are there some certain things that I will see in the oceans which won't be seen in 2D simulations?
So if you write down the QG model of the ocean, which is effectively the 2D equations that I showed, you won't ever get this. Like, it doesn't incorporate waves, and waves are the things that breaks those eddies. It only talks about eddies. So to have the waves, you have to have 3D models, or something close to 3D models, as Mayank discussed some time ago.
Okay, so if there aren't any other questions, we will end this session. Thank you, Rajarshi, for your talk.